Alright, welcome to the Lab 4 introduction video. I'm going to give you a while to do this one because it's a little bit more complicated. And also, for fun, if you would like to, you're not required to, but you can start working in pairs. Just groups of 2, no more than that. But you can work in pairs with other students. So, let me explain that first. So, I'll pretty much allow that for the rest of the class. If you want to work in pairs, I just want to make sure everybody is on the same footing before we do this. And now you're ready. So I want each of you, if you do choose to work in a pair, to submit separately to the autograder, and also tell me in a comment in your code, pick a file or two, and tell me like who you worked with, so that when I see identical code, I don't like try to give you a 0 or something. Okay? So yeah, I can help you transfer code between each other if you don't know how. I can help you with that. You can feel free to post on Discord to find a partner, and I can help too if you are shy. So yeah, let's talk about this. This one is going to be a C++ lab. So you're going to implement an ALU, an 8-bit ALU. So it's an ALU that works on 8-bit numbers. All right, so just single bytes. So run that gimme command, get that starter code, and yeah, what you're going to do is simulate an 8-bit ALU from logic, from those logic gates that we've been talking about. All right, you're going to work bit by bit to do all these things. So yeah, here's your job. I've made you a bunch of files. Here are your files. All right, here they all are. Let's look at a few of them. I want you to read everything and then also read this entire write-up, please. All of your answers are mostly here. All right, so here's the header, and we're making a class that packages together the idea of being an ALU. All right, and we're doing it very low level. So we have 8 bits each, right? We're storing 8-bit numbers. We're working on 8-bit numbers and like 8-bit operands. And that's an array of 8 bools, as you would expect, right? A single bool is a single bit. Cool. All right? And so your 8-bit ALU has a constructor, has ways to load in to your operands, those are your member variables, has a way to compute what you want to compute based on your selector, right? Here are the things that you could do. You can do and or add, and also subtraction. And so I'll have a 2's complement, and then you can like hook into add again. So that's the idea. You're going to compute an answer based on your opcode, and your result is going in this array that the user passes. So you got to fill that. All right. And then also, I'm having you set your flags on instructions. All right, set the N flag, set the Z flag, C flags, B flag. All right, so those are more member variables, and like getters should get the results back. All right, so that's what that looks like. That's what you're implementing. Read the write-up, go through everything. I've given you a lot of I've given you a lot of stuff already. So here's like the constructor that zeroes out everything. The getters are done for you. You got to start here. Fill in these fixed me's. Load the operand 1. Like the user gave you this number, load it into your operand 1 because you're going to need it later. This one, load it into your operand 2. You're going to need it later. All right. And yeah, let's go back to the write-up for a little bit. So every number in this ALU is represented as an array of 8 booleans. So you're getting these operands. It's an array of 8 bools. Those are your 8 bits. All right. And they go in this order. Index I is bit I. So it's kind of backwards, but it's still useful. All right, so bit 0 is this one. This is bit 1, bit 2. So like this is the number 6, all right? Because this is bit 0, this is bit 1, this is bit 2. You read it backwards, all right? Backwards to how you would normally interpret an array. But like we want the indices to be the same as the bit numbers, so it makes more sense there too. So there's a correspondence there, all right? So this is 110. It's the number 110 is in binary, all right? That's how you read it. Note that it looks backwards to you, but you can think of these bit numbers. That's the kind of the trade-off that we're making here. All right, and the ALU gets to do 4 different things. The user either can tell you to and or add or subtract your 2 operands. All right, and the operation the user tells you as the opcode, they need to give you a 2-bit selector value. It's like 00 means and, 01 means or, right? You need 2 bits to choose among, right? To multiplex over 4 different things. So I have like given you a bunch of comments to talk about that in the compute method. So this is kind of what you're getting from these. This is a public method. Like here's your selector based on these values in the selector. remember that like 0, 1 means the selector looks like this. Bit number 0 is a 1, bit number 1 is a 0. Make sure to keep that in mind as you're checking things. So based on the selector, you got to go and, like, the result goes here, shove into the result the answer by, like, telling your ALU to do one of these things. Tell it to AND into a place. Tell it to OR into a place. Tell it to add into a place. Okay? So that's what you're going to do. And then after every operation, you're setting your flags always. Every single instruction is a flag setting instruction for us. You got the N, Z, C, and V flags, and you have to set them after every call to compute. And so you're going to want to do those probably in these helper functions. All right? And or an add, really. Set the flags there for yourself. So the N flag gets set when the result is negative. Go back to the lecture if you want to see, like, what does that mean? It's going to be your highest bit, right? That's a 1 if it's negative, 0 if it's not. The Z flag gets set if your result's 0. The C flag is set if the if there's a carry out of the most significant bit, which only happens during addition and subtraction. And then the V flag is set with when arithmetic overflow happens. All right, so there's a fancy way to check for this that I talked about in lecture, and I think I tell you again either here or in a comment. All right. So yeah, C and V, you only have to ever set it to 1. It's always going to be set to 0 unless you're doing add or sub. All right. And so yeah, what happens, the way the user does things, the way this 8-bit ALU class works is you make an object of this type, and then you load some operands, and then you do a computation with compute. Okay? So this is kind of how that works. The testing file kind of does that for us here. So like here is a test for AND. So like here I am loading 2 numbers into AND. I'm computing based on the selector value for AND, which is 0, 0. Then I'm making sure the answer that I get back, I've made some helper functions to like make it easy for me to compare your giant Boolean values to something that's easier to look at, and like making sure that the N, C, Z, and V flags are set to the right things. Okay, so like those are the kind of tests that I'll be doing. So for example, let's talk about ANDing. All right, let's say that the user loads 2 operands. Loads operand 1, that is this number. Loads operand 2, that is this number. All right, so you're going to have those 2 calls, and they'll be set like this, right? It's 0, 1, 0, 0, 1, 0, 1, 0. So it's like this. 0, 1, 0 is backwards, right? Because this is a high bit. This is bit 7. This is bit 0. Same on this one. It's 1, 1, 1. 0, 1, 1 is the end, right? 0, 1 is the end. It's backward. This is bit 0, bit 1, bit 2. All right? And so the user loads these with the operand loading methods. And then the user will call compute with the selector set to 0, 0, because that's AND. That means AND. And then they're going to pass along where they want you to shove that result in. So this is like your bus in essence. Like this is feeding into some register or something. You want to fill in your result with the 8 bits of the answer. So you're ANDing together those two operands, and like you're computing an answer. Like this is your result. 0 AND with 1. Should put a 0 there, right? 1 AND with 1. Should put a 1 there. Yeah. That's kind of how that works. Okay. So yeah, just remember bit numbers. Like if this is your number, 110, it's the number 6. This is bit 0, this is bit 1, this is bit 2, and so as an array, it's going to look like backwards. It's going to look like 0, 1, 1, and then other things, right? If that's what it looks like. That's how we do it. All right. So yeah, this is your result, which is meant to mean this number. And so this is what you're going to set. You're going to set result, right? The result vector, it's going to be the result array to exactly this, right? Just each bit you do the logical AND on. And like this is the final answer interpreted as a final 8-bit number, if you care. And you're also setting your flags. So N, Z, C, and V are getting set. So this is highest bit is a 0, so 0 here, right? So it's positive. N should be set to 0 because it's not negative. The result is not 0, right? It's not the number 0, so the Z flag should be set to 0. It's false. It's not a 0 result. And this is not arithmetic, so C and V automatically set them to 0. There are no carries involved, okay? So that's AND. So OR is kind of similar, right? Operand 1 gets set to this, for example, and this. For operand 2, the selector is 0, 1, which looks like this array, right? Bit 0 is 1, bit 1 is 0. That's OR. and then you OR these guys up, right? 0, 0 ordered with 0, 1 ordered with 1, 1 ordered with 0. Like, this is your answer. It's backwards. This is like the real number. And so that's going to go into the output, right? That's going to go into the output. And you can, like, in essence, your compute function is going to call, like, OR in this case. You just pass along your res. That's all you do. And then you got to set n, z, c, and v as well. So this result is a negative number. Starts with a 1. So set that. It's non-zero. So z should be set to 0, and again, it's not arithmetic, so c and v should be set to 0. So that's what's going on, all right? And then, yeah, let's do add and sub examples. So let's add together this number with this number. In the arrays, it'll look like this, operand 1, operand 2. Add is 1, 0, so it looks like this, right, as the array, because bit 1 is the 1. And then you're going to add them up. So you're going to have to start with your lowest bits, 0 plus 1. The answer is 1, carry nothing. Then 1 plus 1, 0, carry a 1. 0 plus, you have carry ins and carry outs now. It's going to be a loop, right? You're going to have to loop over these bits in order. Okay, so that's how you're going to do add. And like, here's the answer. And it was negative, so you set your answer to 1. It's not 0, so you set z to 0. There was no carry out of bit 7. If you think about this, this is bit 7, right? 0 plus 0. Like, there is a 1 coming in, but there isn't a 1 going out. So there is, like, this happens, but there is no carry out. And so the C flag is 0. There was no carry out, but the result did overflow, all right? The sum, these are what? These are two positive numbers, and somehow we ended up with a negative number. So the V flag needs to be set to a 1, okay? So that's what add does. And I've given you some comments about all this stuff, so that's how that works. So you can just call off and, or, and add, okay? That's how that works. And then overflow, a trick for overflow for the V flag. An easy way to check it is just check, did the carry in to the most significant bit match the carry out? If it's not equal, the overflow flag should be set, all right? That's how that works, okay? And so finally for sub, if the user asks you for sub, there is no sub method here, but there is a 2's complement thing, 2's complement operand 2, because subtraction is the same as negating operand 2 and then adding, okay? So let's subtract this number from itself. Operand 1 and operand 2 will get set to this. Sub is 1, 1, all right? And then the result, right, you're going to get to compute. You're going to notice it was 1, 1. Oh, no. Oh, gosh. Where do I want to be? Here. You're going to get to compute. You're going to be like, all right, it was 1, 1, so I better 2's complement the operand 2. Like, here's this. Like, do that. I think that will be helpful for you. You can hook it into add here as well, but you need to negate, right? Negate arithmetically your second operand so that you can just use add again, all right? Because then you can just add the thing negative and then it becomes subtraction. All right, so you use that and add to implement sub. And yeah, so you're going to do that computation. I hope you can kind of see how that's going to be implemented. You're going to get this result, all right? And that's 0. So 0 is not negative. It's, sorry, I shouldn't say positive. It's non-negative, and so the negative flag is false. All right, it's not 0. It's not negative. It's 0, and the result is 0. So z should be set to 1, and it did produce a carry out. If you think about it, you're gonna like take this, negate it, add it, and like once you do that operation, there will be a carry out of bit 7. All right, you can do it on paper to confirm that. So you should be setting c to 1. And then the result did not overflow. The carry in and the carry out of the most significant bit, they were set to, let's see. Oh shoot! It says the result did not overflow, so the V flag should be set to either 0 or 1. I'm gonna fix this. All right. So come back later to see what it was. But I guess let's just do it together because this is wrong, right? So did not overflow should mean that it's set to 0. All right, so either I wrote this wrong or there's something weird going on. So 1, 1, 3, 4 zeros, 1, 1, 4 zeros, 1, 0. All right, we're going to subtract it from itself. So we're going to have to negate it, right? How do we negate that? 2's complement is going to be flip all the bits. 1, 0, 1, and then add 1. And so this becomes 0, 0, 1, 1, 1, 1, 1, 0. And then we add them. That's the negated version, all right? This is subtraction. Lightning speed, subtraction. 1, 0. Am I doing this right? Yeah, that's 1, 0. Yeah, this is 0. Carry the 1. 0, carry the 1. 0, carry the 1. The result should be 0, right? 0, carry the 1. 0, carry the 1. 0, carry the 1. So we have a carry 1 out, all right? But the carry in was 1. All right, the carry in matches the carry out. They were not unequal. Or am I saying that? So the carry in was 1, the carry out was 1. So was 1 not equal to 1? No, they were equal. So the V flag did not overflow, so I was right to say it, but it should be set to 0. So pretend that says 0. I will go and change it right after I finish recording. All right, so the V flag should be set to 0 there, just like we figured out. All right, so yeah, overflow in general. Look at the comment. Here's the idea again. Overflow is when the answer can't fit as a signed number into the number of bits we have. So like if you add 2 positive numbers and suddenly it becomes negative, like this one, then it totally overflowed. All right, it was arithmetic overflow. And then similar things with subtraction. All right, so yeah, if you added 2 negative numbers and suddenly we got a positive number, that shouldn't work, right? So an easy way to check for overflow for our 8-bit numbers is to look at the carry in and the carry out of the 7th bit. All right, carry in, check and make sure it's unequal. Right, if the answer is yes, they are unequal, then it was overflowing. All right, so yeah, pretty much your job is to implement everything in ALU.cpp, everything with the fix me. All right, so a lot of these methods are yours, and yeah, just remember that when you're doing sub, you want to like choose complement your operand and then just do add. That should work. All right, so I've made you a makefile that will compile. This make makes the test ALU program that hooks into your stuff, and I have a bunch of tests ready to go. You do not have to make any of your own. You're just messing with the ALU implementation itself. All right, so get all my stuff to pass. Start early. You can see why I'm giving you multiple weeks to do this one, right? Get all my tests to pass, and you are good to go. So I think that's what I wanted to say. Yeah, I'll go and make sure this is set to 0 and when you download the file. But yeah, that's all that I want to say for your lab 4. We're going to do C++ for this one, just to implement at a high level a simulator for this arithmetic logic unit. All right, so ask lots of questions, start early, and I will see you next time.